All right. Hi, everyone. Thank you for joining us for today's HEI Energy webinar. My name is Ayusha Ariana, and I'm the research assistant with the Energy Research Program here at HEI. Today, Drs. Jenn Baka and Sue Brantley will present their HEI Energy-funded research on groundwater quality as related to unconventional oil and gas development in Southwestern Pennsylvania. I'd also like to take a moment to acknowledge my co-organizers at HEI and thank our speakers for joining us for this event. So for some background, HEI Energy is an independent, nonprofit corporation chartered to provide policy-relevant, high-quality, and impartial science. We host educational events such as this webinar and fund research that is selected, conducted, overseen, and reviewed independently of our government and industry sponsors. Research funded by HEI Energy undergoes rigorous oversight by the Energy Research Committee and review by the Energy Review Committee. This graphic illustrates these processes generally. The Research Committee has now completed its oversight of Dr. Baka's research. Early in the new year, the research you will hear about shortly will undergo independent evaluation by the Review Committee. When that evaluation is complete, the final research report will be posted to the HEI Energy website. Before we delve into the webinar, I'd like to make a few housekeeping announcements. So all attendees are muted with no audio for the duration of the webinar. You can turn on closed captioning for the event at the bottom of the screen to the right of the Q&A button. You can submit questions at any time of the event with the Q&A function, and the questions will be reserved for the last 15 minutes of this session. This webinar will be recorded and posted on our website. If you experience any logistical difficulties, please send a message to the host through the Q&A function. We hope you enjoy the event, and we will now welcome our speakers. Dr. Jenn Baka is an associate professor of geography and an associate at the Earth and Environmental Systems Institute at Penn State. She conducts interdisciplinary research on how energy systems impact human-environment relationships and environmental governance. Since 2020, she has been a member of the Environmental Justice Advisory Board for the Pennsylvania Department of Environmental Protection. Prior to joining Penn State, she was an assistant professor of geography and environment at the London School of Economics from 2013 to 2016. She earned a PhD in environmental studies from the Yale School of Forestry and a master's in public policy from UC Berkeley. Prior to graduate school, Dr. Baka worked in the energy industry for numerous years, first as an economic consultant in Washington, D.C., and second as a consultant for the United Nations Environment Program in Paris, France. Dr. Susan L. Brantley is an Evan Pugh University professor of geosciences at Pennsylvania State University, where she also served as the director of the Earth and Environmental Systems Institute from 2003 to 2022. As a geochemist, Dr. Brantley focuses on understanding what controls the chemistry of natural water and how water interacts with the rocks through which it flows. Her recent work has focused on environmental impacts related to the use of hydraulic fracturing in natural gas and oil extraction. She lives with her husband in State College, Pennsylvania, where she watches from afar the careers of her two daughters, both geoscientists studying water in the environment. Welcome, Jenn and Sue.
Thank you for that nice introduction, Ayusha. Are you able to see my slides?
Yes, they're all good.
Excellent. So I will go into presenter mode now. Thank you, everybody, for joining us. It's really a pleasure to be here. And it's a pleasure to share with you the work that Sue and I have been collaborating on that has been sponsored by the Health Effects Institute. Before we dive in, I just want to thank the other collaborators on our team. We have two outstanding graduate students that have been helping us. That would be Owen Harrington and Sam Shaheen. And then Tao Wen, who's an assistant professor of geosciences at Syracuse and a former postdoc of Sue's. He's been helping to lead the charge as well. This was a joint collaborative effort, and it's really a privilege of Sue and I to be here and presenting the work on behalf of the team. So I'm going to give an overview of the project and give you a rundown of some of the social science findings, and then I'll turn it over to Sue, who will be talking about the geoscientific analysis that we conducted. All right, so the objective of this study was to evaluate the relationship and possible contamination pathways amongst unconventional energy development, water contamination and public health in a tri-county region in southwestern Pennsylvania. It's highlighted here in red, Beaver, Washington, and Greene counties. These are some of the most heavily fractured counties in the state of Pennsylvania, and it's really an epicenter of unconventional energy development at this moment with the introduction and opening of the Shell ethane cracker plant that's up in Beaver County. And what we did through this analysis was integrate social science and geoscientific knowledge. And in particular, we did community focus groups, which was the social science method, in each of those 3 counties over the course of 2 years. And we did that to try to get a better perspective on community concerns about this relationship between unconventional energy development and water contamination and public health. And we used that to inform a geoscientific analysis of a large water sampling database. And so I'm going to speak about that community focus group work before turning it over to Sue. All right, so just a little bit of background. So what is a focus group in case folks might be unaware? This is a method of qualitative research, and it works very similar to interviews, except that you're doing it in a group setting. So the purpose is to get together a small group of people who share a common concern and to ask them a set of predetermined questions. So in this case, the researchers act more as facilitators, asking those predetermined questions to get community members talking. All right, and an important thing here is that a focus group doesn't have to be representative per se, so we don't have to gather all opinions on a topic, and that's not what we did, or that's exactly the strategy that we followed in this case, because we were really interested in honing in on community concerns. So the focus group attendees all had something to say in terms of a possible concern they held on this relationship. We didn't have people who had a neutral opinion who came just trying to learn more about this topic, and we didn't have people who thought that there was no relationship. So we really wanted to get a handle on community concerns so that we can do this geoscientific analysis. And often in social science research, you would do a focus group as part of a suite of different methods, because you want to take those public perceptions and analyze them every which way you can, and then do follow-up work to try to address those community concerns. And that's essentially what we are doing here in this study. So the focus group in some ways formed a foundation for the broader research project, if you will, because we really wanted this to be a community-led research project. All right, and just a little bit of background on what we did in these focus groups. We held 6 different focus groups in total over the summers of 2022 and 2023. And we had 1 focus group per year in those 3 counties, Beaver, Washington, and Greene. And in this past summer, 2023, we invited back the participants who attended the focus groups in 2022 because we wanted to share with them our preliminary results of the geoscientific analysis. We wanted to make sure that we were properly understanding their concerns, and then tell the communities first and foremost what we were finding, and make sure that we were on the money. All right. And the sessions went quite a long time, much to our delight and surprise. They went 90 to 150 minutes each. It was not hard to keep people talking. We were doing this research in the aftermath of COVID, so many people commented that it was really nice to get together and come together in person to talk about an issue. All right. And then using qualitative research software, we analyzed the recordings of the different focus groups to identify some key themes and commonalities of concerns. And putting that in academic language, we followed what the researcher Saldana calls an emergent coding scheme. So we didn't go into those transcripts of the recordings looking for specific items per se. We had a generalized set of concepts that we were interested in learning about, but then we populated and expanded that coding scheme based on the community feedback. Okay, and I'm happy to talk more about that in the Q&A if knowing more about this research method is of interest to the group. All right, now who attended these focus groups? So this is just a simple summary table of the attendees in both sessions over the summer 2022 and summer 2023. We had between 6 and 16 participants, which is pretty good. It might not look good from, from a large and quantitative analysis perspective, but from a qualitative perspective, these are good numbers. They skewed largely female and, nearing retirement age, if you will, and with, an average of 30 plus years in the communities. So that's also really good. So these areas of Southwestern Pennsylvania, there's a long history of energy and industrial development in this area. So having a focus group population with that kind of knowledge on the area, I think really added a rich dimension to our focus groups discussions. And we asked a series of 10 questions overall, but the overarching question is summarized up here. So what are the changes that you're seeing in your water? And how do you think that relates to the introduction of unconventional energy development in the area? All right. Now, just getting into some of the findings from the focus groups and going through and reading carefully and coding the transcripts, we identified 6 key themes of the analysis. We don't have time to go through them all today, but the 6 broad themes were the changes that communities are observing to their water, the possible contaminants and possible contamination pathways that they think are responsible for these changes, health effects that they think are associated with these changes, and then getting into some of the changes they might like to see. What are their recommendations for improvement? And then what do they think might be inhibiting how they know about this relationship amongst unconventional energy development, water contamination, and public health? So what are the obstacles to knowledge on this topic? And then what sources of information are they drawing on to form their opinions? So we don't have time to go through all of these in the webinar today. I'm happy to follow up on any of these in the Q&A or after the fact, but I'm going to speak on topics 2 and 3 here in my remaining time. So some contaminants of concern. What I have for you here is a table that summarizes different types of contamination, and then the number of times they were mentioned in the focus groups across the 3 counties. Okay, so this isn't the number of people who said these things, but the number of times this topic was brought up in the course of the conversation at the focus groups. And so by and large, the contamination or the contaminant of concern to communities across the 2 of the 3 focus groups was possible radiation contamination. Okay, and on the left-hand side, I kind of break down, and try to explain why these different contaminants were mentioned and why they were of concern to communities. And you see here in reading these explanations that these people who attended the focus groups, they were pretty educated on this topic. So radiation is a concern because people were concerned about the produced waters from unconventional energy development, bringing up some of the naturally occurring radioactive materials that are in the subsurface waters. And people knew about that and knew about that as a possible contamination pathway in the water handling side of unconventional energy development. And then there was also some concern about chlorine contamination, particularly in Beaver County. And then, with PFAS being a topic of broad public interest at the moment, that was also an issue of concern. All right, but by and large, what communities were most, what they wanted more answers about was potential radiation contamination. All right, and then the pathway of concern. I was alluding to this in the previous slide. People were thinking that there might be possible radiation contamination from wastewater disposal and storage. Sue has more slides on this, but that water that comes back up whole as part of the unconventional energy development process. There's a whole heck of a lot of it, and people were concerned about possible spills and the disposal processes being used in the area. Many people came to us with pictures of what they thought were examples of operators illegally dumping wastewater or spreading it on the roads for for dust suppression. So there was just a concern that if that water might contain some of those radioactive materials, if there are spills and mishandling or illegal dumping happening of this water, that might be a contamination pathway in which communities are exposed to radiation. All right, and then biological extension, what is the health effect of primary concern to people? Or if you're concerned about radiation, that immediately brings to mind cancer. And that, by and large, was the main health effect of interest across the 3 focus groups. And, this relates to the possible exposure to radioactive materials in the wastewater handling, but also at the time that we were doing our research, there was a lot of interest in the local news about instances of Ewing sarcoma, which is a rare bone cancer that impacts teenagers. There has been incidents of Ewing sarcoma in Washington County in particular, and that was getting a lot of press. And at the time that we were doing our research study, the University of Pittsburgh was also doing a public health study looking at this relationship between unconventional energy development and public health in a larger region of Southwestern Pennsylvania. So cancer was an issue, a topic, right at the top of mind for many of the people who attended our focus groups. And then sadly, many of the people who attended the focus groups had many stories about experiencing a rare cancer of them by themselves, and thankfully being a survivor of that cancer, or losing close friends and family members to rare cancers. All right, so that was just a quick summary of some of the main highlights we saw from the focus groups. And I think that this quote really brings it home. This was a quote from someone who attended the Greene County focus group. And they were saying, in Bobtown, which is a community in Greene County, we have lots of kids, unfortunately, at times who've had cancer, childhood cancers, again and again, all very rare cancers and of different types. So they're saying, oh, you're 1 in a million, you're 1 in a million. And they're referring there to public health officials. But how many people can hit the Powerball on one particular street or on one tiny community that has a little over 300 houses? So people in these focus groups kept asking us why, why is it that these seemingly rare cancers that, there's perhaps dozens of cases in the country a year, why are so many of them diagnosed in this small area of Southwestern Pennsylvania? And might unconventional energy be responsible for this increase in cancers as they saw it? All right, so the key takeaway from the focus groups: communities are most concerned about potential radiation exposure from UOGD wastewater management, which may be increasing risks of cancer. And so that's the main takeaway that we summarized from the focus groups and used to inform the geoscientific analysis, which Sue will discuss now.
Great. Thanks, Jen. So if there's a next slide. I'm happy to talk about the geoscientific analysis part of our project. And as a person who studies water and rocks, 2 sort of broad methods of investigation come to mind when you think about the kinds of contamination that we're worried about with UOGD, unconventional oil and gas development. And the 2 methods are fieldwork to study cases on a case-by-case basis. And our group has done some of that, not with this HEI funding, but in the past. And then the other is geostatistical analysis. And the first type of investigation is how you figure out what actually happened in one place, or at least you can eliminate what didn't happen and then come to some kind of defensible idea for what happened. But if you want to understand the prevalence of problems or find out where there may be even ongoing contamination, you have to do something that's more geostatistical. So for this project, we didn't, if you go to the next slide, we didn't do this first topic or investigation, but we did the geostatistical analysis. Next slide. So I thought real quickly, I should just remind everybody what we mean by UOGD, how we develop these unconventional reservoirs. They're unconventional because they're low porosity, low permeability, and the way they are developed in Pennsylvania, in the Marcellus, and in many places, there's a vertical well, and if you hit the button again, Jen, then at several kilometers in depth, the vertical well is actually turned and drilled along a horizontal unconventional reservoir, a reservoir with low porosity and permeability. So the idea is that the kilometers, that blue arrow between shallow water, which is the water we drink, and then the reservoir that's being developed and is being fracked, that blue arrow indicates ostensibly the rock, which is safeguarding the drinking water at the surface. The other part that is safeguarding our drinking water is casings, and that's the other part of this diagram. You can sort of see there are steel pipes that are in place, and they're kind of telescoping diameter, and you can see they're, as much as 24 inches at the surface. That's the surface casing protecting the drinking water. But then when you get down to the bottom, the production casing can be 4 inches in diameter. And between these casings, cement is in place, and this is really what keeps what's inside that well from getting outside and getting into our drinking water. Next slide. So the way that the gas is actually developed, or the reservoir is developed, is along that horizontal borehole, as you can see up there in red. Little tiny bullet holes, so to speak, are put into the casing, and then high pressure water is pumped down there, really large volumes, and when it's high enough pressure, it can actually frack the rock. So you see those vertical fracks. And sand is put in there. You can see the boxes and boxes of sand that are used on a frack site. Sand is put in there so that when the gas is released at the top of the well, when the valve is open, so to speak, the fractures don't close back up. The sand props them open. So the sand is referred to as proppant. Next slide. So what's really different about this fracking, because we've been fracking wells for a really long time, what's different about this fracking is the huge volumes that are used and the very high pressures that are used. And this is from a recent article of the New York Times, just showing from, I think that's 2012 to 22 or something like that. Went from like 1 million gallons up to some of these fracks, the New York Times called them monster fracks, can use as much as 40 million gallons of water. And so you see these impoundments like shown on the slide as well. So next slide. So what the public has been worried about is to make the fracks happen. To make the frack happen, the fractures happen, they put in chemical compounds, and some of these are toxic. They're present at very, very low concentrations, but they're of concern if they get into our drinking water, and you can see that some of them here. So next slide. So if that frack fluid stayed down many kilometers in depth down in the shale, like in the Marcellus here, that would be great. But of course, when the valve is opened at the top and gas comes back up to the top, the gas that we're exploiting, some of that water comes back up. And so in every well pad, and here's one just south of Pittsburgh, 30 miles south, this actually has, I think, 5 or 6 wells on it. But in every well pad, you will see those big barrels, so to speak, or big bins there that collect the water that comes up. The gas is put into a pipeline and moved into the pipeline supply, but the water comes back up as well. And so early on, the water that comes back is called flowback. But over time, it's not just the fracture fluid that comes back, it's water that was originally down there in the shale. And if you go to the next slide, that water is very, very salty. So what we've been trying to do is understand what the impacts of this industrial process is. And one interesting thing to think about in terms of this particular industry is that it's a disseminated industry. So you can see across Pennsylvania here, the unconventional oil and gas wells. Well, these are all gas wells, I believe, the blue. It's disseminated across our state. So it's an industry, but it's disseminated in something like 40 of our counties. And when we're trying to figure out what it's done to our water in some kind of statistical sense, we had to get a lot of groundwater samples. And so we began working with just about anybody who was collecting groundwater in 2011. So we worked with other academics, we worked with government folks, we worked with industry folks, worked with watershed groups, and we compiled a very large data set of groundwater, which groundwater and surface water. Oops, can you go to the previous slide? So groundwater and surface water, that we have like 20,000 data points, and Tao Wen at Syracuse University is really in charge of this. So what we're going to focus on today is in the Southwest, and I'll talk a little tiny bit about the Northeast part of Pennsylvania. These are the two sort of most drilled parts of the Marcellus. So next slide. So we wanted to know if unconventional oil and gas development is affecting groundwater and water wells, and how, and if so. And so we tried to look at either Southwest PA, SWEPA, we call it sometimes, or Northeast PA, NEPA. And we were always looking for evidence from the water chemistry in relation to the oil and gas wells. But we also recognize there's also coal mining you can see on this, and a lot of conventional oil and gas wells as well. Next slide. So some of the species that come up in the production water are shown here. Very high total dissolved solids. So if you hit the advance, it can be as much as 7 times saltier than seawater. So most of it is sodium chloride, which is exactly the salt that is in seawater. But it turns out that there are some fingerprint species. We call them fingerprint species because they're chemical species that help us identify when brine has contaminated something. And in particular, we look at barium, which is another salt, strontium, another salt, and then bromide. But there are also toxic elements such as thallium and arsenic, which are present at much lower concentrations. If you hit the advance, there are also organic compounds in there. And some of these compounds like trichloroethylene, TCE, probably are from the flowback water itself, so the fracture fluids. But some of them, the benzene, for example, could be either from the fracture fluid or from the shale itself. And these, again, are at lower concentrations in general. But if you hit the advance again, also of concern, especially in the Marcellus, is radioactive components, and the principal contributor of radioactivity is radium, again, at a lower concentration than the sodium chloride. Next slide. So we wanted to do a regional analysis and try to understand whether some of these elements show any correlations with development. So in other words, do we see evidence for increases in these species close to some of these unconventional gas wells? So we tried 2 different metrics, either distance to the closest UOG well shown there on the left, or do we see correlations with density of UOG wells within a kilometer? And because there are a lot of measurements that are beneath detection, and because of the skewness of the data, we look at the Kendall rank correlation. So this is a statistic that looks at the ranking of concentrations to get a statistical evidence. And then we were typically looking for a statistical significance, and we always give the p-value here. And we identified in Southwest PA statistically significant correlations between chloride, barium, and strontium, and the 2 metrics. So next slide, please. So why are there these regional increases in salt concentrations? Why in SWEPA, Southwest PA, does it get slightly saltier, very small increases in salt, by the way, slightly saltier in the groundwater, closer to unconventional gas wells? Next slide. It turns out that what we think is going on is that there are isolated problem locations. It's not like regional, it's really just a couple problem locations. And so to find these problem locations, we worked with Jessie Lee in our Information Science and Technology program and collected, she came up with a technique called what we call the sliding window, where we can look for hotspots of stronger correlation by moving a window across our data set. So this is just a map of water analyses in latitude and longitude. So it's just a map of one part of Pennsylvania. And then as this sliding window goes across in each of the locations, we look to see if there's a correlation between the salt concentration and either the distance to a UOG well or the density of UOG wells. And then in essence, for each window, we get an average of the correlation. And then we're able to map that, as shown in the next slide, to identify where there are hotspots of correlations. So this map now is showing those 3 counties in Southwest PA that Jenn has already alluded to a couple times. And it just shows hotspots for the increasing chloride concentration with increasing density of UOG wells within a kilometer. And the darker colors show where chloride increases with the density, with an increase in density of wells. And we only emphasize the darkest hotspots because these increases are very, very small. These are not anything you could taste. This is very, very small increases of sodium chloride. And so we believe that the regional increase in salt concentration with UOG wells is really caused by a very small number of hotspots that we think we're identifying here. Next slide. So just as sort of an aside, we did this in earlier work with methane. So that was everything I talked about so far was with chloride, but now we're doing it with methane, where again, we see increases in methane with a small number of UOG wells. And in SWEPA on the left, you can see that the hot spots where methane increases close to these wells there's a small number of these spots. But if you look up in Northeast PA, which is on the right, we actually see this as more of a problem in Northeast PA than Southwest PA, which is very interesting because Southwest PA has been so developed for oil and gas. We might have expected more problems, but we saw less problems with methane. And actually, Sam Shaheen has hypothesized that it may be because there's been so much earlier legacy development in SWEPA that much of the methane in the intermediate depths has been already extracted, and that wasn't really the case up in the northeastern Pennsylvania. Next slide. Okay, but let's go back to the chloride hotspots, which is the main part of this story. So what can we do with our geostatistical technique to understand what happens with the chloride hotspot? So if we go to the next slide, we tried different approaches to figure out what was going on. On one approach, we do a machine learning based approach where we use the computer to look through all the data and try to estimate what is going on. And we use a technique called non-negative matrix factorization. So we look at the groundwater chemistry, and then we try to figure out what sources can explain that chemistry, and then look at the end member compositions of those sources. And what we observed in Southwest PA is there's a really good signal from road salt. So road salt puts sodium chloride into the waterway and in the groundwater. There's chloride from rainwater, but then we also see a very strong signal from the brines. So these production waters that I've been talking about. Next slide. So that's one line of evidence that it's the brines that are causing these chloride hotspots. Another line of evidence is that when we look at the median barium concentration in our groundwater, we see that it's 23% higher within a kilometer of any well pad where there was a spill that was bigger than 250 gallons. And you can see on this map data from Patterson et al. In 2017, the dark red squares are spills bigger than 250 gallons. If we do the same analysis for spills that are bigger than 500 gallons, the triangles, it's an even stronger correlation. And so this is another line of evidence that the spills are in the specific incident and locations are causing this, even this regional chloride increase that we see. So we can also do a back of the envelope calculation and convince ourselves that there's enough salt in a spill of 250 gallons to explain the kind of effects we see in the groundwater. Next slide. Well, we've done some other techniques where here's the median concentration of barium. I think this is actually statewide, but if I showed it to you for SWEPA, we'd have a similar result. And if you look at the horizontal black line in each of those colored rectangles in each of the graphs, barium's on the left, strontium's on the right, you can see that the median is higher for when the water samples have UOG wells within a kilometer than the blue color, which is where the water was sampled further than a kilometer. And then you see the same thing for the strontium. So the mediums are always higher when you have more UOG wells. No significant increases were found for casing or cementing violations statewide. So if we look at the DEP, Department of Environmental Protection data set, where there's casing or cementing violations, we don't see any effects like what I'm showing here. So it doesn't look like the spillage is happening in the subsurface. But if you go to the next slide, Jen, if we look at the same kind of a plot as a function of where spill violations are documented, we see an even larger effect, namely the barium is higher close to the well pads with spills than farther away, and the same with the strontium. Next slide. And then this is a little bit more complicated finding to describe, but we can actually calculate the increase in concentration of either chloride or barium or strontium with each additional UOG well within a kilometer, and then look at that correlation coefficient. You can look at the equation there on the left, and the correlation coefficient is the beta. It's the regression coefficient. I misspoke there. At any rate, when we look at those values, the increase in concentration, you can see that the increase in concentration is larger, again, for the spill violation. So hit the button again, Jen, than it is if we just look at it as a function of the UOG well density. And if we look at the coefficients, the beta values for barium versus strontium, their ratio really looks like the ratio in produced water, which is also shown at the bottom of that slide. Next advance, please. All right, we also look to see if barium and strontium concentrations increase near problem impoundments. And in particular, in Southwest PA, there are 8 impoundments that have been reprimanded by the Department of Environmental Protection in 2014, and they're shown in that slide. One of them is the Jaeger impoundment, and there's a book written about this, a Pulitzer Prize winning author. The book's called Amity and Prosperity, where the liner was ostensibly allowing leakage. And again, we see that median barium is 34% higher within a kilometer of these impoundments. Next slide. And if we look at the hotspot analysis again, this is the hotspot for chloride versus density of UOG wells. When we compare the hotspots to groundwater flow modeling in the literature from Jim Sayre's group with Mario Soriano, they show places that they predict from physical modeling combined with machine learning where water should be vulnerable to spills, and it seems to overlap with some of our hotspots. So next slide. In addition, one of these, if you go back, please, one of these hotspots, chloride hotspots, overlaps with one of the problematic impoundments, the Carter impoundment. Next slide. So why might salt concentration be important, especially for a health effects conference like this one? So next slide. The toxic element concentrations in the brines are low, and they're generally not detected in analyses. So these are some of the ratios of different elements that are toxic to the chloride. And even at the detection limit, some species can increase health risk. So what we did was, if you go to the next slide, we used the ratio of these toxics to the chloride, and go to the next, hit the advance, you can hit it again. And what we were able to do is say, we know how much thallium, for example, there is per chloride, the thallium concentration to chloride concentration. And we can multiply at times the increase in chloride that we've just calculated in our hotspots per UOG well within 1 kilometer. And what we can calculate is that the thallium concentration exceeds the EPA maximum contamination limit in 3 of our 5 hotspots shown there circled on the left. And we can look, if we see arsenic, beryllium, and cadmium, they also exceed 75% of the EPA limit in at least 1 hotspot. And if you advance one more time, we've tried to do this for radium. The problem with radium is we don't have really good radium to chloride concentrations. It's very variable across the Marcellus play, but it is clear from the data, from the ratio of radium to chloride multiplied in this way, that there is potential for radium concentrations that could be higher in some hotspots, higher than the EPA MCL. Next slide. Thallium ingestion has also been associated with low birth weights. And then just this year, a study completed by the University of Pittsburgh School of Public Health and funded by the Pennsylvania Department of Health concluded that infants within 1 mile of 1 or more UOG wells during production phase were 20 to 40 grams smaller at birth. So that is at least an association that could be suggestive that the thallium could be a problem. The Pitt study also concluded no association between UOGD and childhood leukemia, brain and bone cancers, but they concluded that children within 1 mile of 1 or more UOG well, active well, had 5 to 7 times the chance of one kind of cancer, namely lymphoma. And the more intense the UOGD activity, the greater the risk. But the risks were very, very small. So you can see the risks because this is such a rare cancer. And there was no association for other environmental hazards except a very small suggestion for brain tumors correlating with uranium mill tailings, which is a different story entirely. Next slide, or the advance. I just wanted to point out, we are showing correlations here. There are other sources of pollutants that are going to be impacting people close to UOG wells, and there's hazardous air pollutants that have been reported by the industry, and some of them I've listed are there. And so if water quality is a problem in terms of some of these health effects, I'm suggesting that the toxic elements that I've mentioned here could be problematic, and we would like to study that more. But there are other avenues of exposure. Next slide. So the geospatial conclusions, wastewater mishandling is the likeliest mechanism to increase salts in groundwater near UOGD. And this is really consistent with community concerns. And the salts could be accompanied by problematic species such as thallium, arsenic, and radium. And unfortunately, these really large data sets that we have don't have large data sets for these very elements. There are differences in the Northeast and the Southwest, which are really interesting to us in terms of understanding what's going on. This is related, we think, to hydrology and also to legacy extraction, and I mentioned one of those. In general, we agree with the physical hydrology modeling. Households down gradient from the spills and impoundment leaks are the most likely to be impacted. So thanks, and I think I go back to Jen's concluding remarks.
Yeah, so thank you. Just to wrap up and bring the social science back into conversations with the geoscience, to emphasize again, we do see a convergence between the community concerns related to wastewater management being a likely contamination pathway. That's something that the geoscientific analysis is also emphasizing, but there's a divergence in terms of the contaminants of concern. The focus groups were primarily concerned about radiation exposure, and the geoscience analysis was using salt species, as a fingerprint analysis for possible contamination for other hazardous substances like thallium. Thallium was not something that came up in the focus groups, so something that we're taking back to the communities as part of our broader research is that, paying attention to some other hazardous species in addition to radiation would be worthwhile. But the thing to emphasize here is that we need to do more follow-up water testing and community outreach to advance this study. So the geoscientific analysis was identifying those hotspot regions through a water sampling database that was just one sample at one point in time. So we would like to go out next and do some follow-up testing in those hotspot areas to further triangulate our results. And I think that, one key takeaway from an academic perspective from this study is that there's I would consider this a very successful collaboration among social scientists and geoscientists. And, I think it's a good example of a study that could address community needs from a variety of perspectives. So we very much thank you for taking the time out to join us today. And we are happy to answer any questions that you might have. Thank you very much.
Thank you, Jenn and Sue, for your fantastic presentation. So now we are going to be moving into the Q&A session with our speakers for the last 15 minutes of this webinar. Dr. Donna Voorhees, who directs the Energy Research Program here at HEI, will be moderating the discussion. So please feel free to send any additional questions you have through the Q&A box, and we'll do our best to get them. Thank you.
Great. Thank you, Ayusha. And Jenn and Sue, thanks for a terrific presentation. We have questions coming in on both the geoscientific analyses and the focus group work. And I think I'll start with one of the focus group questions, if that's all right. Curious about how you recruited attendees for the focus groups and whether you needed to account for any kind of bias in the participation among focus group members.
Yeah, thank you so much for that, Donna. So we did extensive outreach. So this is an area where I've been conducting research for a good 7 years now. So I'm grateful to have earned the trust of some of the community groups working out in the area. So we work with them to advertise through their networks. In addition, Penn State is a land grant institution. So we have extension agents all throughout the state. So we work with them. And then also some of the hidden gems that, I discovered in the course of this project. So I'm more of an energy person, not a water person, but every county has a county conservation district and a water person, a water expert in that office. So that's a government official. So they also helped us to do outreach and recruitment. And then in terms of the bias, like I said in my slides, we were most interested in bringing together people who had concerns about this relationship. But, we take all that information in, and then we try to triangulate it. And we worked as a research team to try to, figure out of the concerns, which ones would most likely be related to unconventional energy development versus some additional type of industrial development. So we try to, look at the problem, look at the feedback from a myriad of lenses to try to identify the top concerns that were likely most relevant to this relationship we were studying. But we appreciated all the information, but then had to sort it in accordance with the goals of the research team.
Great. And we have one that overlaps the focus groups and the technical work. Asking about the scale of the risk perceived by focus group members versus what the science is actually saying to you. Sorry, the question just disappeared. That was the general question. What is the science actually saying to you? And what additional work do you all recommend to explore the discrepancy? I mean, I think you've been very clear that the scientific aspects of your work were very much focused on identifying sources of what's in water and geochemical analyses of water, not risk assessment per se. But what can you say about making that connection in future work?
Yeah, and that's a really good point as well. So I think Sue did a good job of emphasizing that the statistically significant results that we're finding were just a handful of locations and small in magnitude. So we're not talking about, deep water horizon type of spill here, where there's a sensational area that is, high in statistical significance and large in geographic scope. So that is something that we work to emphasize in this summer's focus groups. But then also, I think it's important And this is something that came back from the communities. They were happy to, have people have researchers come and listen to them. And, we didn't stop the clock at any certain time. And, when somebody is having to relive the experience of going through cancer treatment themselves, or having experienced a loved one going through cancer treatment, we didn't want to cut them off and fall back into, academic language. Like in that instance, everything is significant. So we wanted to make sure that we took their concerns seriously and addressed them point by point, in our follow-up work.
Great. Thanks, Jen. Thanks for that thoughtful reaction. That was great. Okay, I'm going to switch to a technical question. Sue, you touched on this. I think it's worth elaborating. We're being asked, or you're being asked, what consideration was given to proximity of conventional oil and gas wells and impacts on groundwater? How does this impact the findings, or how is it separated from unconventional gas development? Would you mind elaborating on that?
Right. So one of the reasons we were interested in SWEPO is because of all the legacy development. And so the grad student who's led this, Sam Shaheen, has worked really hard to look at, water chemistry versus, coal versus conventional oil and gas wells versus unconventional. And then we typically look for, what the statistical significance is and how big of an effect we see. And it is true that we can pull out and see some effects of conventional wells, but in SWEPA, there are so many conventional wells because this is the area really, it's just south really of the area of Pennsylvania where the oldest oil well, the Drake wells, that was, I guess, 1859. So there's just so many conventional wells that finding a really strong statistical correlation with chloride concentration is really difficult. It's like looking at a rug that's completely covering the landscape. So we don't see a strong correlation or effect for the conventionals in SWEPA as we do for the unconventionals. Now, having said that, in Northeastern PA, we published a paper, and you can look at the actual numbers. I can't ever remember all the details, but there's a small number of unconventional gas wells that we correlated with some what we think could be putative leakage into groundwater in Northeastern PA, but we also saw a small number of conventional wells that showed similar correlations too. So the questioner is very correct to identify this, but interestingly enough, in SWEPA, it's just hard to pull it out for the conventionals because there's so many of them. And actually, so many of them, we don't even know where they are, presumably.
And I guess a related question, I'm getting a more general question of, did you find a strong positive spatial correlation between high chloride, bromide, strontium, and thallium in groundwater?
So we didn't look at spatial correlations of thallium because we have such a small number of analyses of it in our big data set, or a small number of detections in our data set. So, we just can't do that big data analysis. That's precisely why we're looking at chlorine, barium, and strontium, as we get so many more, we have so many more analyses. So we didn't do anything like that with thallium. So I wasn't sure what the rest of the question was.
That was the total question. If the person asking wants to elaborate, please add it.
Yeah. Just to make it clear, what we did was we saw the statistical regional correlations with the chloride, barium, and strontium. And then we said we can't do it for thallium because we don't have enough data. But if thallium to chloride, that ratio is constant in the production waters, and we can get that, I don't think I said this, we got that ratio from the production water database from the USGS for this part of Pennsylvania. We got that ratio because they have a lot of data in the production water database. If we know that ratio, then we can take our statistical correlations and start to make some predictions for thallium. And what we'd like to do is go back and take water chemistry and actually measure thallium and maybe get a data set that has a little bit more data volume.
Great, thank you. Yeah, this isn't a question, but we do have one participant saying that they've personally overseen numerous spills and hydrologic investigations in Northwest and Southwest PA at conventional and unconventional sites, and they are observing through their work issues with wastewater handling. So that seems to parallel what you're talking about here. There was also some questions about I think it was slide 22, and you don't need to go back to it, but the very specific question about the meaning of the p-value, is it p less than 0.005, or did you really mean 0.5%?
I guess I'd have to go back to see exactly, but I mean, in general, we're always looking for confidence limits 95% or above. So that's essentially, sometimes it's even higher than that, and the p-values can give you that value. One of the questions I saw were asking about the blue color versus the red color, and it gets a little tricky because of just the way we define our metrics. But in general, if it's red, it's showing you that the salt is increasing in concentration in the groundwater nearer the UOG wells. And the blue means the opposite, which is really strange. And that's either just something to be ignored because there's not enough statistical significance, or, I mean, you could come up with reasons why the hydrology could explain some effects like that. But we've never tried to make much of a conclusion from anything other than the really darkest red hotspots.
Great, thank you. All right, we are also getting questions about policy and asking for your perspective on the policy implications of this research. Anything here that would inform decisions about setback distances for gas infrastructure, preventing spills, or somehow, some kind of policy action to prevent spills, more transparency with the public on these kinds of events?
So
I'm not sure your research says anything about transparency other than you've been very transparent with the research you're doing, and we'll be presenting all the results.
Well, I've done work, on case studies, and then there's this statistical work where we're getting the data really through the DEP. But case studies, you can't do those unless you have transparency. So I really do push for transparency, and you need both case studies and statistical. So transparency is one thing. In terms of setbacks, I'm not speaking for Jenn, but I think 500 feet, which is like the Pennsylvania closest building, that's the setback. That's way too short. One of our case studies, we could show that not only methane, but also one of the compounds that was used in the UOG moved more than 2.5 kilometers. So the setbacks really should be longer, in my opinion.
Yeah, and if I can add, I can follow up from the focus groups. The need for transparency is definitely one of the key concerns under that category of what changes would you like to see. But I think what our results are also showing is that the need for continuous water testing, if we're going to transform rural society basically into an industrial zone, well, to minimize the negative impacts of that, then we need to be, monitoring for environmental impacts continuously over the lifespan of that industrial process. And that was another need expressed in the focus groups.
You also asked about wastewater management, and I think about what you do when you're cooking in your kitchen. Everybody cooks, everybody spills. We are going to have spills, and I don't think you can litigate against that or regulate against it. It's going to happen. There's going to be spills, and this is one of the big Achilles heels of this whole industry. I mean, there's so much water that comes up, and it's very, very salty, and it has other things in it as well.
So we have less than 2 minutes left. I know this research benefited from data from the Pennsylvania Department of Environmental Protection. I'm wondering if you could speak to that, the source of the data, and then speak more generally to where to go next. I know you had some ideas in your last slide, but what is there left to do with the data that's existing before you go collect original data? Where the next step for you, the next step for other research teams, what would you recommend?
So I didn't say where the data comes from. I mean, this is a huge data set. When oil and gas companies drill, they are going to be liable if they contaminate somebody's drinking water. So what they do is they pay professional geology consultants to go out and sample waters, groundwater, water wells, springs within a certain distance, and the different companies use different distances. And then they take those waters, they give them to a commercial analytical certified laboratory, environmental laboratory. And then those data are given to the regulator, the DEP, before the drilling, so that if there is someone later that says my well was contaminated, they can take a sample in the same way and compare it. And then they can either be presumed liable or presumed not liable for whatever happened. So all those data go to the state, and they used to go on paper, and they were not being released to the industry or to the public. And so we early on, because we started working with the public and, many years ago in 2011, and we realized that, this is really a gold mine. We asked the state, could they give us the data on paper, and could we, type it in and put it into a database? And that's what we've been doing since 2011. I pay undergrads to type it in, and then we try our best to get it all accurate. And that's where those 20,000 data points came from. Penn State undergrads, it costs, I think, $10 per analysis to get it into the database. And that's way cheaper than going out and getting new analyses. And these data, it's in the best interest of the companies for these data to be really good data, because they compare them later if there's a complaint.
Great, thank you. And I'm so sorry, we're out of time. We have more questions. So thank you again so much. Ayusha, Ariana put a feedback survey in the chat. We hope you'll fill that out. And again, I just want to thank Sue and Jen so much for a terrific presentation, for everybody who participated. Thanks so much.
Thank you.
Thanks so much.